Okay, so we are going to take notes over Chapter 7, Section 1, and the essential questions that we're answering in the section are: what is the relationship between a planet's orbital radius and period? What is Newton's law of universal gravitation and how does it relate to Kepler's laws? And why was Cavendish's investigation important? You do not have to write these essential questions down in your notebook. They're just to help us know what we're kind of focusing on as we go through the slides. So we're going to start out with Kepler's laws. Kepler's first law states that the paths of the planets are ellipses with the sun at one focus. So on one side of that ellipse. And there is a video here. I'm going to try to play it and we'll see how this goes here. Okay, well, I'm going to exit out of our slideshow here. Or maybe not. Okay. All right. And I'm going to just exit out here and I'm going to open up the video. And the sound, I'll try to kind of give you a synopsis of the information here. All right. Kepler's first law.
Kepler's first law states that the paths of the planets are ellipses, with the sun at one focus.
So if you couldn't hear that, it just says that Kepler's law shows that the planets have an elliptical path.
All the planets in our solar system revolve around the sun in elliptical orbit.
And that the sun is the focus on one side of that ellipse.
Like planets and stars, comets also orbit the sun in elliptical orbit.
Okay, and we can see.
Comets are divided into two groups: short period comets and long period comets, based on orbital periods.
Now, I am not worried if you know the difference between a short period comet and a long period comet. I'm just trying to get with this Kepler's law for you to understand that the planets orbit around the sun in elliptical orbits.
Comet Halley, with a period of 76 years, is an example of a short period.
Okay, so that's what we should need to understand about Kepler's first law. All right, going back to our slides. Kepler's second law states that an imaginary line from the sun to a planet sweeps out in equal areas in equal time intervals. So if we look, each section of this, the time is the same for each section, and the area, if we were to calculate this full area, these would be equal. And the times that it takes a planet to get from here to here or here to here are the same. So I'm not going to show the video. It's just going to say the exact same thing that I'm saying right here. Okay. And then Kepler's third law states that the square of the ratio of the periods of any two planets revolving about the sun is equal to the cube ratio of their average distances from the sun. Thus, if the periods of the planets are TA and TB, and their average distances from the sun are radius A and radius B, Kepler's third law can be expressed as follows. So this one has an equation. So it's just stating that the ratio between the periods of two planets squared is equal to the radius of each of those planets, radius from them to the sun, or that distance, cubed. Okay, and this is important because if we don't know one of these, if we know the other three, we can isolate the variable and find it. Okay. And then this is just going to talk about the same thing. It's just going to move the planets and go through the same thing. So I'm not going to play the video for you. All right. Then we have Newton's law of universal gravitation. So beginning in 1666, Isaac Newton studied planetary motion and concluded that an attractive force must act between any two bodies with mass. The force of attraction between two objects must be proportional to the object's masses, also known as the gravitational force. Okay. The law of universal gravitation states that objects attract other objects with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. So what do we understand about this? That the masses make a difference. So if we have two objects that are the same mass, like here, they have a different force than when we have to an objects that have different masses. Okay, so it's saying that the attraction is proportional to their masses. So the bigger the object is, the more attractional force it has. So you can think of this like two planets are the same size, or the sun, the earth and the moon. There's more gravitational force because the masses, when we multiply them, are bigger. And then that our force of gravity is inversely proportional to our radius. So the farther away two objects are from each other, the less gravitational force there is between them than when they're closer together. We can see this with the moon. If you understand that the earth has tides, and those tides have to do with where the moon is in its orbit around the earth. And when we have more planetary bodies, so for example, when the sun and the moon are lined up with the earth, the tides are bigger because there's a bigger gravitational force, more mass. Okay, because the distance, and when the planets are closer together, the planet and the moon are closer together, more gravitational force than when they're further apart. All right, and then this is the equation. The force of gravity is a gravitational constant, the mass of planet or object 1 and object 2 divided by their radius between them, that distance between them squared. And this g is a constant. We looked at it in the book, and it is 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. That's the unit. It's kind of an odd unit on it. Okay. And then universal gravitation and Kepler's law. Okay, so universal gravitation and Kepler's third law, Newton's law of universal gravitation, can be combined with the definition of a period to find the period of an object orbiting the sun. So we can use this to figure out how long it takes for a planet to orbit the sun. And that period is 2 pi times the square root of the radius from the sun to that planet cubed, divided by that gravitational force, gravitation and the mass of the sun. Okay, squaring both sides makes it apparent that this equation is Kepler's third law of planetary motion. The square of the period is proportional to the cube of the distance that separates the masses. Okay, again, just like in other chapters, I do not expect you to memorize these equations. You would be given them on a test or a quiz. And then the last thing is what's called the Cavendish experiment. Okay, and the Cavendish experiment, they used lead spheres and a mirror, small and large ones. And this was used. Okay, so I'm just going to explain the Cavendish experiment rather than showing the video, because the sound isn't very good in it. But how it worked is they had this rod that was suspended by a string, and it sat in a bracket where it was allowed to move horizontally. And they fixed 2 large lead spheres close to the small ones, and due to the gravitational force, the small lead spheres moved closer towards the large lead spheres. And there was a mirror attached in the center where it rotated on a line, the rod did. And then what Cavendish did is he measured this angle where the movement of the spheres was, because once they had moved to a spot where they were balanced in their gravitational force, and they stopped moving. And he took that angle and put it in to the law of universal gravitation equation, and he was able to come up with a value for G, that one that we use, at 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. And so that's where that number came from. Okay. And that is it for our notes. If something doesn't make sense or you're not sure what I'm asking on something, please feel free to come and talk to me and I'll happily give more explanation on the notes. Thanks.